Welcome back to CE 5331 Probabilistic Methods for Civil Engineers. In the last lecture, I introduced you to the course and some very basic, gave some very basic definitions of what uncertainty and variability is. So in this class, and I also stressed upon you or tried to highlight how probabilistic methods are useful for civil engineers and how their use is going to be even more important into the future as data-driven modeling or big data becomes more the norm in civil engineering practice. So we'll continue our discussion of probabilistic methods in this lecture, and what I want to do in this lecture is introduce you to the basic definition of probability. So without further ado, we talked about stochastic variables. The word stochastic stems from the word stochasticos, or to aim at. If you think of an archer, the archer's goal is to get the arrow right at the bullseye, but there are other factors, sometimes factors that we don't know of. For example, your body, the archer's arm could shake a little bit. There could be wind. There could be factors such as those that affect, the elevation of the land. All of these can affect the ability of an archer to get that arrow to the bullseye. So there is an element of chance. So anything that has an element of chance is randomly defined. The outcomes of the stochastic events cannot be determined precisely. So just by looking at the archer aiming that arrow, it's unclear whether it's not possible for us to say for sure that the archer will get that arrow at the bullseye. So stochastic events are basically events whose outcomes cannot be determined exactly. So they can only be characterized in a probabilistic or a statistical sense. Stochastic approach is best suited when the inputs cannot be specified precisely. So the inputs either have errors or limitations, and also because there is variability, natural variability associated with those inputs, and the relationship between the inputs and the output are not known precisely. If the inputs are stochastic, then the output is also stochastic, because if you cannot determine the input exactly, it is even if you have a deterministic relationship, or even if you have an exact relationship, it is difficult to still quantify what the output is. Again, civil engineering processes and phenomenon are seldom known with certainty, and they exhibit variability. Uncertainty, as we defined it last time, is the situation where we don't have complete information about a process, phenomenon, or a variable of interest. This arises usually because of insufficient measurements or instrumentation errors. So by taking more measurements, at least in a frequentist sense, at least when we define objective probabilities, by taking more measurements, we are able to reduce that uncertainty. Variability, on the other hand, is the natural fluctuation in an observed process, phenomenon, or a variable. And variability is something that we cannot reduce because it's intrinsic to your system, or it is part of your system. But by collecting data and making measurements, we are able to better characterize that variability. So in terms of probability, both uncertainty and variability are treated the same way because their net result is the same. The net result is that the phenomenon of interest or the variable of interest cannot be predicted with a high degree of accuracy. We can only talk about predictions in terms of the likelihood or the chance of the variable taking a certain value. Statistical randomness, we talked about this as well. Statistical randomness occurs when we cannot describe the state of the variable that the variable will take. So let's look at a watershed. A watershed essentially is defined based on a pour point or an exit point or a drainage point. This is where the water drains out of your watershed. And if I take that point as a reference, what watershed does is it defines a contributing area such that any water that falls, any rainfall or any water that falls in that watershed, if it's not lost otherwise, will eventually make it down to that point. So we can define watersheds with regards to any point of interest to us. And if we take that point and then we ascertain what is the upstream or the contributing drainage area that will contribute to the flow at that point. In other words, if it were to rain in that contributing area, all that water would show up at that point. That point is called a watershed. And based on the soil moisture characteristics in that watershed, we can go back and define some states. We could have a dry state. A dry state is where the moisture in that watershed is fairly low. A normal state, which is typically where the soil moisture of that watershed is. Again, this is a random variable. That means that there is no one value that defines normal. It could be within some range. And then wet conditions, or the wet state, can be defined as having a lot of moisture or above normal moisture in that watershed. So given that our watershed will always be in one of these states, either it's dry, it's normal, or it's wet. Okay, and also our watershed cannot be dry and normal at the same time, because we have some very definite cutoffs which tell us what's dry and what's wet and what's normal. So even if we know whether the let's say the watershed is dry, normal, or wet, even if we know in this month, let's say the watershed is dry, it doesn't give us the ability to predict whether the watershed is going to be dry, normal, or wet the next month, because there could be rainfall, or there probably is no rainfall. So depending on how much moisture is added to that system, we really cannot define what our state of that watershed is going to be in the future, in the next month or the month after that or so. So we cannot say with absolute certainty what the state of the system will be in the future. And what we can best do is predict the likelihood of being in each possible state. We do know that it has to be in one of these three states next month. So we can say what is the likelihood, or what is the chance that it is dry, it's normal, and it's wet. So in a frequentist approach, the way we do that is we take measurements over time, and we take all the historical data that we have, and we say how many times has the watershed been in the dry state, how many times has the watershed been in the normal state, how many times has the watershed been in the wet state, and then we calculate the relative frequencies. That is, we divide the total number of times the watershed has been in the dry state by the total number of observations. Same thing for normal and wet, and we get probabilities. Okay, so there is a 20% chance that the watershed is dry next year, and a 10% chance that it is wet next year. That means that if we look at historical observations, 20% of the time the watershed was dry, 10% of the time the watershed was wet, and then for the remaining 70% of the time the watershed was in the normal state. So frequentist approach, as I said, we count the frequency at which the system has been in a particular state. We use the frequencies from the past to make predictions about the future. So if the system has been wet 10% of the time and dry 20% of the time in the last 50 years, based on all the measurements that we've made, we can define and say the long-term frequencies are the dry state is 20%, wet state is 10%, and the normal state is 70%. So we can use this information and make a prediction and say next month there's a 20% chance that we are going to be dry, 10% chance we're going to be wet, and 70% chance that we are going to be normal. And it so happened that we might get a very big rainfall event, and our watershed might end up being in the wet state, even though we only gave a 10% chance for that based on our historical records. And the temperatures might go up, we might have an unusually hot time of the year, and the watershed might end up being dry, which only had a 20% chance. So these chances are based on historical observations. These chances are our best guess of what the likely state is going to be, but they're not exact. They're not predictions in an absolute sense, because there is still a chance that even though we are thinking very likely our watershed is going to be in a normal state, there's a finite possibility that it could either be in the wet state or in the dry state. So that is what long-term frequencies help us. Of course, we can probably refine this prediction a little bit if we have a covariate or if we have something else, some additional information. For example, if we know that this month was wet, because this month has already happened, if we know that this month was wet, we can go and calculate what are called as conditional frequencies. That is, if this current year is wet, then what the next year is going to be. And these conditional probabilities could be the dry is 5%, wet is 30%, and normal is 65%. So essentially, what you're saying is, given I have that extra information that this year was wet, what's going to happen next year? And given that it's wet, we have reduced our probability of dry state being from 20% to 5%, because we knew a wet state will likely follow a wet state because of persistence of hydrologic phenomenon. And similarly, we have upped that probability of the wet state from being just 10% to 30%. And of course, the normal state has been down by from 70% to 65%. So knowing the fact that this year was wet is an additional piece of information that's used to calculate conditional frequencies, whereas the long-term frequencies are simply calculated based on all the information that's available. So if we didn't know that whether this year was dry, wet, or normal, this would be our best estimates. And if we knew our current estimate, our current year was wet, then we can update those probabilities and create new estimates based on this additional information that the current year is wet, and that's called a conditional frequency. The frequentist approach again assumes that the past is a good indicator of the future, and the way we calculate the conditional frequencies is very similar to the way we calculate long-term frequencies. In the long-term frequencies, we calculated the number of times the system was dry, number of times the system was normal, the number of times the system was wet, and divided by the total number of observation to get these long-term frequencies. In the conditional frequencies, we first filter out the current year when the system was wet, and then we just use that data and say, given that the current year was wet, how many times was the subsequent year dry, and how many times was the subsequent year normal, and how many times was the subsequent year wet. And again, we calculate the relative frequencies by dividing it by the total number of times when the event was wet. So we'll do these calculations in the class as well, but I just want to introduce at this point these concepts. So probability is a fundamental construct to study stochastic systems. Our probabilities can be objective or subjective. Objective probabilities are obtained by observing the phenomenon either in time or in space. For example, if you have a geotechnical site assessment, the soil is going to say, if we have like say sand, silt, and clay in our soil, we can it's likely going to say sand in the future. Like if it was sand today, it's likely going to be sand in the future. But spatially, I'll have some places where there is sand, some places where there is silt, then there's some places where there is clay. And so we can define our three states as sand, silt, and clay, and find out the relative frequencies by making measurements in space. Subjective probabilities, on the other hand, that's how you get objective probabilities, either by making measurements in time or in space, or both sometimes. And subjective probabilities are probabilities that are defined by an expert. So, what is the probability that the bridge will likely collapse after the next storm event? So this is, you could ask an expert and say, what do you think is the chance of this bridge collapsing? The expert might run some analysis, or based on the observations of the bridge, or when the bridge was built, the kind of loads that bridge took, he or she might come back and be able to say, yeah, there's a 20% chance, or there's a 10% chance that this bridge might fail for one reason or the other. And really, it is not based on repeated measurements of that bridge being failed, but it's an assessment based on what the expert is thinking will likely happen given the type of loadings the bridge is going to experience in that storm event. So subjective probabilities are different from objective probabilities, but we all tend to use subjective probabilities, because if I ask you what is the chance that it's going to rain tomorrow, you will be able to say, some percent based on the time of the year, looking out and seeing whether it was sunny, whether there's a storm system brewing somewhere close by. So those kinds of factors get factored in to get your subjective probabilities. Objective probability, on the other hand, is something that you get by making repeated measurements. So if you had repeatedly observed whether it rained or not for the last several decades of your existence, whether it rained on a particular day in Lubbock, then you would go back and use those and say, how many times did it rain, how many times did I observe, and the ratio of that would give you your objective probability. Our focus in this class will largely be on objective probabilities. There are methods to deal with subjective probabilities, or integrate subjective probabilities with objective probabilities. That's called Bayesian statistics, but will not be going into the class. But nonetheless, the probability concepts that you're going to study in this class, or that we're going to study in this class, are very vital for making Bayesian calculations or performing Bayesian analysis. So one other good reason to have a very strong fundamentals in probability. When we talk about probabilities, it's also important to know that we are calculating our probabilities based on data, and the data is obtained by observations or by doing an experiment and collecting some data. So one thing that becomes very clear, or becomes very evident, is that we cannot physically monitor all possible states the system has been in the past, okay? Because we have instrumentation limitations, we have money, or fiscal and logistic constraints, and we are constrained by nature and other forces. So for example, if I take a flow in the river, we might be making measurements every 5 minutes. So every 5 minutes I observe the flow rate, and that is a sample that I'm getting. But what happened to the flow between those 5 minutes? That is part of the unknown population. Okay, so what we measure is a sample, and the range of all possible values the random variable has taken or can take in the future is referred to as the population. So let's say we have measurements for the last 10 years of wind loads on a bridge. What happened before 10 years, what happens in the future, all that is part of the population. So similarly, I took 4 boreholes to measure soil shear at a site, but conceivably I could have put hundreds of boreholes and probably thousands of boreholes if I got a really tiny borehole. And what does the soil look like in those areas where I have not sampled as part of the population? And so when it comes to sample, we know everything there is to be known about the sample. The only thing we probably don't know about the sample is the measurement error. But that uncertainty associated with measurement error is often small, and we neglect it. But what we are really interested in probability is not the sample, because we have all the information there is to be about the sample. What we are really interested about is what is the likely probability of a population? What is the probability of things that we have not measured or have been unable to measure? So that's what we are after. So we're always after the population, and we use sample as our guide to make predictions about your population. So if you take this class, I'm going to sample your understanding of the knowledge of your knowledge of this subject by making periodic assessments. I'm going to give you an assignment, a project, a journal article review, so on and so forth. And based on that assessment, based on that sampling, I'm going to assess how well do you know this material. Okay, so I am trying to infer your ability to understand material that you've not been tested on, based on some tests or some samples that I've given. Again, is what probability is about, and what we are after. So we're always after a population. Measurement of all possible values of a population is called census, and as you know, in the U.S. And in many other countries, we do census once every 10 years to count everybody, the entire population of the country. But if you go to census.gov and look at census data, you will see that there are estimates of people that the Census Bureau makes every year, and that's based on a small sampling that they do at different parts of the country. So again, our sample is all known. These are the observations that we have made, and the population is the large unknown, or the large set from which we obtain this smaller subset of samples, and that's what we are going to use to make our inferences about our population, or to make predictions about our populations. So understanding sample versus population, again, is a very important concept that you should be clear about as to what a sample is and what a population is. So typically, if you've collected data, you just have a sample. Very rarely that represents the population. And if you're doing statistical analysis, your interest always is in population, seldom is it on the sample. So what is a random variable? Random variable is a variable that can be in one of the multiple non-overlapping states. So again, I showed you the watershed example. In the watershed, we had dry, wet, and normal states. And so those were three non-overlapping states, which means that if the watershed was dry, it could not be wet at the same time. It makes no sense in saying that the watershed is dry and wet, and we know all the possible states the variable can take. So we knew that, if we were to define the dryness, or if we want to define the moisture in that watershed, we would define either it would be dry, wet, or normal. So it had to be in one of those states, as we defined it. But we cannot exactly predict the state of that variable in the future. Again, given we knew what the state was today, we could make some estimates of what is the likely state in the future, but we cannot be absolutely certain that if we were wet this year, we are going to be wet next year, or so on and so forth. So there is always an element of uncertainty, or we cannot exactly say what state we are going to be in. Okay, we can, however, assign probabilities, or the relative frequencies to which of the likelihood of being in various states. A random variable can be continuous or discrete. Continuous random variables take an infinite number of states, because if I say temperature, flow rate, wind speed, they vary. There are an infinite number of values that these continuous variables can take. Same thing with soil moisture, like shear stress. A lot of the variables that we use in civil engineering tend to be continuous, because they can take infinite set of values. We might not be able to measure all those values, and We might have instrument limitations which allow us to only measure it to a certain accuracy, say the second decimal place or the third decimal place. But nonetheless, it is possible that if we had more accurate measurement, we perhaps could have been made, we could have probably seen that the value actually had values in the 5th, 6th, 10th, or even 50th decimal place. So continuous random variables take an infinite number of states. The discrete random variables, on the other hand, only take a finite number of states. Again, this could be a large number of finite states, but nonetheless, they are finite. So, for example, I could be standing at a levee and seeing whether the water was below the levee or it flew, or it was flowing over the levee. So I have two states. So one state where the water is below the levee, this is the state that we want, and then one state where the water is flowing over the levee, which means that the levee was not able to keep the water from moving downstream. So that's a binary variable, or we have two states, a state where there is overflow or there is no overflow on the levee, and such a variable is called a binary variable, or a discrete variable that can take two states. On the other hand, we could also be counting the number of vehicles at an intersection. We could have one vehicle, we could have 0 vehicles, we could have 10 vehicles. Over a period of time, we could have had even 100, 200, 300 vehicles during a rush hour. That number could probably be even larger. So we could have a large number of vehicles, but all those vehicles are discrete. We cannot have 30.5 vehicles crossing our intersection in that time. So we have a countable system. So the same thing. The number of hurricanes or Category 5 hurricanes would be a countable number in any given year, and or number of houses that have been damaged. Again, you can't have half a house that's damaged. So either the house could be partially damaged, but if it is damaged, it's damaged, or if it's not damaged, it's not damaged. So construction engineers might be interested in saying, what is the percent of houses that were damaged as part of the hurricane, or what is the probability of a certain house being damaged given its location and proximity to the coast. So those are discrete random variables, and I gave you some examples of continuous random variables. And again, the random variable represents the population and not the sample. We may collect a sample associated with that random variable and then use that sample to make inferences about the larger population. So again, there is nothing random about a sample except perhaps for the measurement errors that are involved in it. So given that we have a random variable, and we say that the random variable must always be in one of its possible state, again, dry, normal, and wet, then the sum of the probabilities, so if we say the probability or the relative frequency with which my system is in the dry state, the normal state, and the wet state, the system has to be in one of these states. So my probability should always sum up to 1. Okay, and at best the system is not in this state, or the other end is that the system is always in this state. So 0 and 1 represents a situation where the system is never in the dry state, and 1 would represent the system is always in the dry state. So each of these probabilities always varies between 0 and 1. The 0 and 1, which are the bookends, represent certainty or absolute certainty. So a lot of times when we talk about probabilities, we are talking about it being very close to 0 or very close to 1, but never fully in 0 and 1. So, but nonetheless, the values that your random variable can take for each state is the probability is between 0 and 1, and the sum of all those probabilities should be equal to 1. The sum of all probabilities being equal to 1 comes from the fact that all our states are mutually exclusive. That means that if it's in one state, it cannot be in another state. And they are collectively exhaustive. The collectively exhaustive part means that the system has to be in one of these states. We just don't know which state it's going to be tomorrow or next year, but we know for a fact that it's going to be either dry, normal, or wet. So that is what the collective, mutually exclusive and collective exhaustive state say. So we can define a random variable by setting up the mutually exclusive and collectively exhaustive states. There could be an infinite number of mutually exclusive states. And they can all be collectively exhaustive, or they could be a finite number of mutually exclusive states, which are collectively exhaustive. So the two rules are the probability of being in a given state is always between 0 and 1. So you cannot have probabilities less than 0 or negative values. Neither can the probability take a value greater than 1, because probability by its very definition is a relative frequency, or the number of times over all the observations that the system has been in a given state. And then the sum of the probabilities over all states should be equal to 1, because the system has to be in one of those states. It cannot be in any other state, so by its very definition. So the two basic rules of probability are that the values of probabilities, which are the relative frequencies in an objective sense, are always between 0 and 1, and the collectively and the sum of the probabilities must also be equal to 1, so they are collectively exhaustive. Probability, again, in an objective sense, is viewed as a relative frequency of an event occurring, so it represents a long-term behavior. And again, if it is impossible, then it has a probability of 0. For example, if I have 2 dice, I cannot roll a 14. It's impossible, so that probability would be 0. And knowing that the sun is going to rise every day is almost a certainty. We know it has happened for so long that we can pretty much take that for granted. So that would have a probability of 1. And if I flip a coin somewhere, there is a 50% chance that it can be heads, or 50% chance that it can be tails. So that represents an even chance. And of course, for other probabilities, they are somewhere between being impossible to being certain. So there is some latitude as to where they are. Okay. Relative frequency is used to calculate that probability. So let's say we have 30 days of rainfall data, and we observed rain for 30 days at a given location, and we saw that we saw some amount of rain for 3 days. So the probability of the rain is 3 out of 30, which is 0.1. So what does this 0.1 mean? What this 0.1 means is that in the long run, if I were to make these observations over a long period of time, let's say 365 days or a year, or for 10 years, like 3,650 days or 10 years, excluding the leap years, I will see that there will likely be rainfall for 365 days, or about a tenth of that time. So in 10 years, if this were to hold true, month in, month out, then in the long run, I would see that 10% of the time that I've observed, there is going to be rain. Okay. Usually and incorrectly, we tend to interpret this to mean that there is a 10% chance of rainfall tomorrow or any other day. And that is not really the strict definition of probability. The probability in a relative frequency sense means that what is the long-term behavior? Like, if we say, 100-year flood, it doesn't mean that we get that flood once every 100 years. It just means that in 1,000 years, we are likely to see that type of flood, or a flood of that magnitude or higher, greater than about 10 times or so. It doesn't mean that we are going to see like clockwork exactly 10 times, or that we are going to see exactly 365 days of rainfall in a given 10-year period. If those probability were to hold true, there is still a likelihood that I might see more rain, less rain, but that is what is the chance I'm giving. There is a 10% chance of seeing very likely that I will see 365 days of rainfall in that 10-year period. So again, To summarize those two basic rules, the probability is always between 0 and 1. The sum of probabilities of all mutually exclusive states will be equal to 1. So in our rainfall example, you would have probability of rain plus probability of no rain is equal to 1, because in a given day, either you have rain or you have no rain. So it has to be in one of those two states. Again, the way we measure those probabilities in an objective sense is by using relative frequency, that is counting number of times the system, number of days where it rained, number of days where it did not rain, and divided by the total number of days that we have observed, that we have made observations. So the basic concepts of probability that you should know after this lecture is the difference between a continuous and a discrete variable. Continuous variable takes in finite number of states. Discrete variable takes a finite number of states. So if you can count the states, it's discrete. If you cannot count the states, or it's continuous, or if it takes a very, 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 very long time, probably in your lifetime you won't be able to count all the possible states that a continuous variable can take. It might take a very long time for you to count the number of discrete states, but they are still countably finite, as they say in statistics. The difference between a population and a sample: the population is the larger subset of that random variable, or all possible states that the random variable can take over time or in space, and a sample is a small subset that we have observed or measured of that population. So again, there is nothing random about a sample except perhaps for a measurement error, but we want to take that sample and make inferences about our population. You want to know what a random variable is. A random variable is a variable that we cannot determine the value of that random variable with a high degree of certainty. So we can only state what are the likely states of this random variable, or what is the range of the values that this random variable can take, and assign probabilities for a given value that this random variable is likely to take, or a given range of values this random variable is likely to take. Possible states of a random variable are mutually exclusive and collectively exhaustive. Mutually exclusive means that if the random variable is in one state, it cannot be in another state. And collectively exhaustive means that a random variable has to be in one of those states, that define that system or define that variable. We also looked at probability definitions, subjective and objective interpretations. Subjective interpretation is an interpretation that you subjectively say what is the chance of, or the likelihood of something happening, and the objective interpretation is more the relative frequency of observations, and saying if I were to observe this random variable for a long period of time, or if I were to make these measurements over and over and over again, how many times am I going to see the random variable being in a certain state? And that's what the objective interpretation of the probability is. And the objective interpretation is what is the basis or the cornerstone for that frequentist approach that we are largely going to study in this class. So this lecture, our focus is on probabilities and the rules of probabilities, the two rules of probabilities. Probabilities being between 0 and 1, and probability being for each state being between 0 and 1, and the sum of the probabilities being equal to 1. And also I defined what a random variable is. I mentioned what objective and subjective probabilities are, and most importantly I defined what the population in the sample is. So in the next lecture we will explore a few more rules associated with probability, especially as it relates to multiple random variables.